All right, in this video here, we're going to look at a couple examples of finding the inverse of a function. Now, if you didn't look at the other video that I did where I kind of go through the steps, finding the inverse is a three-step process. So I went through those three steps and kind of explained what's going on with them. And in that video, I also did a pretty simple example of finding an inverse function. So if you haven't watched that video yet, you might want to do that where you hear me explain the steps and what's going on here. And then in this video, I'm just going to go ahead and do a couple more challenging examples of finding the inverse of a function using those basic steps that I talked about in the other video. All right, so my first example here, find the inverse of f of x equals x to the fifth minus 3 all over 2. All right, so I want to find the inverse of that function. So the first step to finding an inverse, that f of x there, that's kind of bulky and kind of a pain to carry around when we're doing the problem. So the first thing I do is rewrite this. Instead of f of x, I just make it y. All right, so y equals x to the fifth minus 3 all over 2. Right, and that's just a convenience thing, so I don't have to write f of x every step through the problem. I can just write a y instead. And then at the end, I'll put that function notation back into it. That's like the very last thing that we do is switch it back to the f notation. All right, so y equals x to the fifth minus 3 all over 2. My second step, which is the key step to finding the inverse of a function, is to switch all the x and y values. All right, so everywhere I see a y, I put the letter x, and everywhere I see an x, I put a y. And everything else stays exactly the same. So instead of y equals x to the fifth minus 3 over 2, I get x equals y to the fifth minus 3 over 2. Right? And again, the reason we do that is because inverse functions switch your inputs and outputs. Right? They do the opposite of what the original function does. And so if we need to find the inverse, we switch the inputs and outputs. We switch the x and the y. And then, so that's my second step. That's my key step there. After I do that, my last step is to solve this equation for y. Right, and I say it's the last step. Usually that takes several steps of work to actually accomplish. It's not just usually a one-time thing and like, oh, one more thing and then I'm done. And depending on how complicated that original function is, this could take 1 or 2 steps. It could take 5 or 6 or 7, depending on what algebraic stuff you need to do here to isolate that y, get that y by itself. Right, but that's our last thing we need to do here. Well, almost the last thing we need to do. Right, so now it's just doing a bunch of algebra to get y by itself on one side of the equation. All right, so here I've got this fraction. I got y to the fifth minus 3, all of that divided by 2. So to get rid of that fraction, to get rid of that divided by 2, I need to multiply both sides of the equation by 2. All right, so I get 2x equals y to the fifth minus 3. All right, so I clear out the fraction first. I clear out the denominator by multiplying that denominator to the other side of the equation. All right, so 2x equals y to the fifth minus 3. All right, now I have y to the fifth minus 3, so to get rid of that minus 3, I have to do a plus 3. And just remember, when you're doing all this stuff, it's almost like you're just solving a regular equation. It's just that you have an x and a y in there. And so, when I do 2x plus 3, I don't actually add those together. I just have to write that as 2x plus 3 equals y to the fifth power. All right, so I got 2x plus 3 equals y to the fifth, so couple steps here, multiplying the 2 to the other side, adding the 3 to the other side. Just like when you're solving an equation, you do the opposite thing. Instead of dividing by 2, you multiply. Instead of subtracting 3, you add 3. All right? And now we almost have the y isolated, right? But that y is still being raised to the fifth power. All right, so how do I undo a fifth power? Well, there's a couple ways you can think about it. You can think about it in terms of a root, or you can think about it in terms of another exponent. I'm going to do it in terms of a root because that's the way that I usually handle these things. If I have a fifth power, the thing that's going to cancel out that fifth power is the fifth root. Right? So what I need to do then is take the fifth root on both sides of this equation. So it's going to be the fifth root of 2x plus 3 equals the fifth root of y to the fifth power. All right, so I do the fifth root, and the entire left side of the equation goes underneath that root. The entire right side of the equation goes underneath that root. Right? I'm allowed to do that as long as I do the same thing on both sides of the equation, and whatever I'm putting there applies to that entire side of the equation. Right now, on the right side, the fifth root of y to the fifth power, well, the reason I put the fifth root here is because the fifth root cancels out the fifth power. Right? Anytime you're trying to cancel out an exponent, you can use a root to do that. It's just that the root that you're taking has to match the exponent. Right? If this was a y to the second power, I would do the square root. If it was a y to the third power, I would do the third root, and so on. All right, so I get the fifth root of 2x plus 3 right? Making sure that whole thing is underneath the root equals just y. All right, so I have now isolated the y. So if you watch the other video that I did with the pretty simple linear equation, that one did not take quite as many steps to get the y isolated. Again, depending on how complicated that original equation is, finding the inverse can be more or less complicated. This one was a little bit more complicated than that one I did on the other video because we ended up with that. We had the fraction here. We had that fifth power that we had to take care of. Right. The other way, I mentioned that there was two ways you could think about this. The other way would have been, just to make a side note here, if I do y to the fifth power and raise that to the 1/5 power, the power to a power, when you multiply them, 5 times 1/5 equals 1. So those would cancel out. As long as you do the 2x plus 3 in parentheses to the 1/5 power on the other side of the equation, that would also be correct, right? Because if you recall, with the rules of exponents and how they relate to roots, the 1/5 power corresponds to the fifth root, right? Those two are mathematically the same thing. So they both mean the same thing. Whichever one you choose to use when you're doing this should be okay, right? So you can have either y equals the fifth root of 2x plus 3, or you could have y equals 2x plus 3 in parentheses raised to the 1/5 power, right? These two things mean the same thing. Like I said, usually I do this stuff in terms of roots. That's the way I tend to see it better. And so I use the fifth root instead of the 1/5 power. But if you use the 1/5 power to cancel out the 5, just put that 1/5 power on the other side of the equation and you're fine, right? That's okay. All right, so again, either one of those is okay. So I end up with y equals the fifth root of 2x plus 3. So I've isolated my y. Now the very last thing I need to do is rewrite this in terms of the function notation, right? Remember, originally we had f of x and we changed the f of x to a y. Well, now that I've done all this work to find the inverse, I need to write it back in the function notation. So I write it as f inverse of x equals the fifth root of 2x plus 3. And there's my inverse of x to the fifth minus 3 over 2. All right, so that's my last step. I don't want to leave it as y equals. I want to rewrite it as f inverse of x. All right, and now I've got the inverse function to my original. Right, and notice the relationship between the inverse and the original. Right, the inverse, I have something raised to the fifth power. Well, here I have the fifth root. Those are opposites of each other. Right, I have a minus 3. Well, here I've got a plus 3. Those are opposites. Right, I have something divided by 2. Well, here I have the 2 multiplying the x. Again, they're opposite operations. That's the relationship between inverses and, between two inverse functions. Everything is the opposite. Right, here, first thing I do is raise something to the fifth power. Here, the last thing I do would be take the fifth root. Right, the next thing I do is minus 3, plus 3, divide by 2, multiply by 2. Right, so that's our relationship between inverses. So one example there, I'm going to pause the recording, erase this one, and then do another example where we find the inverse of an even more complicated type of function. All right, we have up here, find the inverse of f of x equals 2x plus 3 over x minus 1. Right, so here we have a rational function, which is one of the more difficult types of functions to find the inverse of, just because the algebraic stuff that we have to do to solve it gets a little bit stickier, a little bit trickier. That rhymed a little bit, that was kind of cool. All right, so f of x equals 2x plus 3 over x minus 1. First thing, same steps that I did on that last example. First thing, change the f of x to a y. All right, so y equals 2x plus 3 over x minus 1. All right, so we want to get rid of that f of x just so it's more convenient to work through the problem. So y equals 2x plus 3 over x minus 1. Next step, interchange the x and the y. All right, so wherever the y is, I put an x. For every x that I see, I put a y. So it's 2y plus 3 over y minus 1. All right, so every y becomes an x, every x becomes a y. Right? Don't make the mistake that I've seen some people do in the past of just take one of those x's and change it to a y, but leave the other x as an x. Every x gets changed into a y. Right? And this is the first example we've seen where we've had more than one x in our equation, but that's what happens when we have that. Right? Every x we switch to a y. All right, and now what I need to do is solve this equation for y, which you can see just by looking at it, that's going to be a bit difficult because not only do I have two y's in the equation, but one's in the numerator of the fraction, one's in the denominator. So how in the world am I going to get all this together into a single y equals a whole bunch of other stuff? Right? There's a way to do it. It's just a little, algebraically tricky. All right, so first thing that I do, anytime I have an equation that involves a fraction like this, I'm going to take that denominator and multiply it over to the other side. All right, just like in the last example we did, the denominator was a 2, I think it was, and I multiplied 2 to the other side of the equation. Well, now my denominator is y minus 1, so I'm going to multiply the y minus 1 to the other side. So it's going to be x times parentheses y minus 1 equals 2y plus 3. Right? When I multiply that y minus 1, it cancels out that denominator, and the y plus 1, or sorry, the y minus 1 gets moved over to the other side. Right? So x times y minus 1 equals 2y plus 3. All right, so first step, got rid of the fraction. That's a good start, right? It's going to be hard to solve for y when I have a y in the top and bottom of the same fraction. But now that I don't have a fraction, it looks a little bit more manageable, right? But still, there's a ways to go until I get the y by itself. All right, so next thing I need to do is basically simplify this left side by distributing that x into the parentheses, right? So x times y is going to be xy. X times minus 1 is just going to be minus x equals 2y plus 3. All right, so xy minus x equals 2y plus 3. And anytime you're finding the inverse of a rational function like this, where you have x's in the numerator and denominator, you're going to follow the same basic algebraic steps to find the inverse. Right? So you can kind of use this one as a pattern. For any function that looks like this, you're following the same basic steps here. All right, so xy minus x equals 2y plus 3. All right, so now what I need to do is get all my y's together on the same side of the equation. Right, because I have a y on this side and I have a y over there on the right side. So I need all the y's on one side and I need all of the things that don't have a y on the other side. And here it doesn't matter which side of the equation you want to bring the y's to and which side you put the other stuff. I'm going to bring all the y's to the left side and put everything else to the right side. All right, so this minus x here, I'm going to add that x over to the right side of the equation. This xy, I'm going to leave the y on the left side. And the 2y, I'm going to subtract that to bring it over to the left side. All right, so I end up with xy minus 2y equals, let's see, so the x's here got canceled, the 2y's, I have x plus 3. All right, so I have a positive x plus a 3 over on the right side, and a positive xy, and then minus the 2y over on the left side. All right, so I got all my y's on the same side of the equation. That's good. Now, what we have here, and depending on how this plays out, this could be easier or more difficult, but xy minus 2y, if this was like 5y minus 2y, well, I would just combine those and make that 3y, and then just divide the 3 to the other side, and I'm done. Right? In this case, though, since I have an xy minus 2y, I can't just combine the x and the minus 2. That doesn't quite work. So the little algebraic thing that we do here, when we have the two y's on the same side of the equation, in order to get that into a single y, is to factor the y out of here, right? So the xy and the minus 2y, they have a common factor of y, right? So I can pull out the y, and it's y times, and I don't think this is going to give me enough room to write the whole thing, but oh well. So it's going to be y times parentheses x minus 2 equals x plus 3. All right, so I get when I get those y's on the same side of the equation, I factor the y out, right? Remember, factoring a common factor is like doing the distributive property backwards. If I distribute that y back into these parentheses, I would have x times y and then minus 2 times y, which is what I had here. All right, so I pull out the y, I get the y times x minus 2 equals x plus 3, and then I have just a single y here. To get that y by itself, I need to divide both sides by this x minus 2. Right, by whatever's in that parentheses there, so I end up with y equals x plus 3 divided by x minus 2. All right, and now I've got that y isolated. It took some work, right? It took some algebraic manipulations to get there, but like I said, anytime you have a rational function like this and you need to find the inverse, you're going to do very similar algebraic manipulations all the way through, right? It's going to be basically the same steps with just different numbers thrown in there on the x's and the y's, right? So if you're trying to do a problem like that, you can use this as a model and just kind of go through and do it, right? And then the very last thing, y, I want to change back to the function notation. So this is now f inverse of x equals x plus 3 over x minus 2. All right, so this would be the inverse function of f of x equals 2x plus 3 over x minus 1. All right, for rational functions, it's not quite as easy to see the relationship between the original and the inverse. You see some of the same numbers there, the 2 and the 3, but it's not as clear-cut as some of the other examples that we've looked at as far as how those two relate to each other. All right, and just remember, with something like this, this x plus 3 over x minus 2, you can't cancel out the x's there because of the plus and the minus that are in the numerator and denominator. So this is your final result. All right, so that's a couple examples of some difficult, or not difficult, but more challenging types of problems of finding the inverse of a function.